So, as Holly said, my name's Martin. I'm the Engineering Practice Manager here at Engineering New Zealand. Thank you for signing into the latest one of the Lessons to be Learned series. I'd like to introduce Alex Gray. He is a past president of the New Zealand Concrete Society, which is now the Concrete New Zealand Learned Society. He's spent over 40 years working as a civil engineer and a project manager, and he's been involved in major construction major infrastructure projects, including the Terrace Tunnel and the incrementally launched bridges down in Tauranga Gorge. He's lectured on risk management for construction projects, and he's here to share some of his knowledge today. And I'll hand it over to you now, Alex. Thank you.
Thanks, Martin. Well, I guess the first fundamental question from people, and it's just going to my first slide, why study engineering failures? And I've been doing it for years. I started off at the University of Canterbury in my last year with the late Professor Harry Hopkins, who had a unit called History of Civil Engineering. And we actually studied a number of failures, a couple of which I'll be talking about today. But the key reason for studying failures, in my view, is to learn from other people's mistakes. And the Tacoma Narrows suspension bridge, to me, is a classic example. Also, you need to realize the fallibility of human beings when everyone's everybody, especially when under pressure. And during construction, this may apply even more. Even experienced engineers have made mistakes. Design mistakes are common as well. And when multiple causes join together, this is often called a Swiss cheese model. However, in some cases, there's only a single cause, and examples are such as earthquake, scour, or ship impact. When I went through varsity way back in 1972, there was no such thing as risk management. It's now commonplace in all projects. The last project I worked on, the risk management file ran to about 10 pages, and each quarter we tended to just focus on the key risks. Finally, something for clients as well as engineers. Under the new Health and Safety at Work Act 2016, all participants in a project, including the client, may now be held liable if they do not take all practicable steps to ensure no harm occurs during construction. And probably a good example of this is a farmer who hires a fly-by-night cowboy contractor to cut down some trees for him, and the contractor has a horrible fatality. In the old days, the farmer could just wash his hands and say, "Oh, it's not my fault, it's the contractor's fault." Well, nowadays, the farmer would be expected to make sure he engages a competent contractor to review his methodology and maybe even his health and safety plan, so that he is fully aware of the contractor's expertise in carrying out the project. Moving on to the next slide, some of you in Wellington may recognise this eagle. It was erected by Weta Workshop, and it stood there for 1 month before it fell down during a relatively moderate earthquake, which was centred in Eketahuna. And this collapse of the eagle is actually a good example of the Swiss cheese model. The key factors involved in this were as follows. The design was carried out by a competent Wellington consultant. However, Weta Workshop said they didn't need the consultant to supervise construction. They would do it themselves. There was a design mistake in that 4 of the 9 wires holding up the eagle were actually stressed to the beyond the recognised safety limit for the wires. Another factor was that one of the wires was not installed at all by Weta Workshop. And another significant factor was the crimping tool used by Weta Workshop staff was faulty and did not crimp the wires properly. Finally, Wellington Airport did apply for an exemption for a building consent on the grounds that this 1-ton eagle was artwork, and this was granted. Well, I think you'd agree with me, looking at this large eagle, that it's a bit bigger than artwork, and when it fell, fortuitously, there was only one small group at 3:52 in the afternoon who were affected, who only suffered minor injuries. So there's a significant lesson here in that things under public display that weigh a ton should be properly supervised. Going back to my background, this was a very high profile job, which I was lucky enough to be in charge of as the site engineer way back in 1983. For those of you who are not familiar with incrementally launched bridges, this photograph shows the principle quite well. Basically, the bridge is cast behind on the abutment and post-tensioned with a launch nose and then launched over the piers using stainless steel bearings and Teflon pads, which are fed in to reduce the friction. The main advantage of this incrementally launched process is visible. Oops, I've missed a slide. Is the I've gone too bad. Is the fact that the bridge doesn't need any false work, and we were going over the State Highway 2, which was a very busy highway, and there wasn't room for false work. I was also involved in the terrace tunnel construction, and as you can see from this photograph, we had some problems building the tieback wall. The key issue was that the designers expected the wall to be built from the top down using stressed anchors, but they had also specified a very high quality architectural finish. And as you can see on the left-hand side where my cursor is, there are D32 bars at 100mm centers around each anchor. And if we'd gone top down in stages, every one of those would have required to be butt welded and x-rayed before going down further. So the contractor elected to build the permanent wall full height from the bottom. So that section there is actually 14 meters high. To support the ground in the meantime, we had temporary ground anchors using the anchor holes going right down to the anchor drive, which was 70 feet or 20 odd meters back from the wall. But unfortunately, we didn't connect the precast anchor blocks to the shotcrete. And so as you can see, during the winter of 76, the ground slipped behind the shotcrete, it fell down. And to cut a long story short, the wall was supposed to only be 600mm thick, and in some places it's 2 meters thick. This wall was cast without a back shutter up against the country, and so we filled this shutter very slowly when it was 2 meters thick. This is a positive story of an engineering project which is still in use today in Auckland. The Grafton Bridge in Auckland, construction started in 1908, unfortunately using an Australian contractor, probably because there weren't sufficient major contractors in New Zealand at the time. And the bridge has got a 93-metre main arch span, which was, when it was constructed, was the biggest reinforced concrete arch in the world. Now, the Australian contractor wanted to make sure he was doing things properly, and as there were no laboratories for civil engineering materials in New Zealand in 1908, he actually sent samples of the sand and aggregate to the University of New South Wales for testing before any of the concrete was poured on the site. And the other thing that's critical when you, and interesting when you look at this photograph, there is no crane visible. Somehow or another, all of this concrete was poured by hand. Here is the opening photograph of the bridge on the 26th of May 2010. As you can see, lots of people are celebrating. The good news story is that Auckland City Council elected to use reinforced concrete rather than steel because they believed it would last longer and require less maintenance. And that's certainly true because Grafton Bridge is still in use today. And now that it's been strengthened with carbon fibre, it can still be used by heavy vehicles such as buses. And right in the top corner here, you can actually see a windmill. This gives you an idea just how long ago this bridge has been built. And if you're building bridges for those younger engineers, you're expected to design it to last 100 years. So design it to last like Grafton Bridge. Now we move on to the first rather sad story, the Westgate Bridge collapse in Melbourne. And I studied this collapse when I was at university in Canterbury in 1972. And the west gate of the bridge was collapsed in 1970 with 35 deaths. And at the time of the collapse, they were joining two halves of the 6-lane structure together with a 110-metre span, 50 metres up in the air. At the time of the collapse, the contractor had no prior experience in doing this. And the big problem was that the Melbourne temperatures on the top flange were a lot higher than what existed on the bottom flange. And so the flanges were distorted. And with the site engineer's approval, they were using large concrete blocks to try and move the flanges down together so they could be bolted together. The design itself was also under strength. And the reason there were so many deaths, unfortunately, was the lunch huts for the workers were actually underneath the span that collapsed. A very tragic accident. Now we move to New Zealand, and this is the Bull Bridge collapse, State Highway 1 in New Zealand, which collapsed in June 1973. There were no deaths, fortunately, but as you can see, for a major state highway bridge to collapse, this should not happen. And fortuitously, there were no deaths. When it collapsed during a storm in June 73, it was collapsed by a bus. And the only person on the bus was the driver. And somehow or another, he was able to swim to the bank and be rescued by two locals who happened to, and this was all at night, who happened to be available to rescue him. Since then, both Transit New Zealand and now Wocket Kotahi do much more regular scour measurements to ensure that this sort of accident doesn't occur again. If you drive across this bridge at the southern end, you will notice that the handrails are different, and that's because this section of the bridge had to be rebuilt. Now we go on to a much more serious bridge collapse, and this one I feel for the engineers involved because it's an incrementally launched bridge, and I cut my teeth in Nowronga building incrementally launched bridges. So this was a 300-metre launch bridge collapse in South Africa in 1998. There were 14 deaths, and as you can see, a major collapse, and principal causes were the lack of competent personnel in supervision. But like all collapses, there were more to it than that. The main cause of the collapse was that the launch bearings were incorrectly placed. If you follow my cursor, this cross-section is of the Nowronga bridge, where the launch bearings were put under the web, which is the correct position because you need the strength of the web. And in Jaka, the launch bearings, for some reason, were installed underneath the bottom of the box, which is much weaker. And this is the wrong place for the bearings. And unfortunately, this was not noticed. And when we look at the Jaka bridge collapse, other causal factors, they are as follows. The design was not peer reviewed. The principal designer was not registered, CPN, and she had only 3 years postgraduate experience. Tragically, she died in the collapse. The site was over 4 hours drive from the design office, and this is part of the Swiss cheese model because when I built the bridges at Nowronga, I didn't realise how advantageous it was to have the designers a 20-minute drive away. The cracks in the bridge deck occurred 1 month before the collapse. The site advised the design office. The senior partner in the design office did some calculations and without a site visit, instructed launching to proceed. The contractor was also negligent, as a competent contractor would not have proceeded with the launch with significant deck cracking visible. Other causal factors were the steel launch nose was not stiff enough, the deck slab was under-designed, there was some incorrect feeding of sliding pads during the launch, the temporary works were not properly designed or reviewed by a consultant. And at the end of this story was that ultimately, after 10 years wrangling, there was no criminal prosecutions in South Africa. However, the senior partner was fined $5,000 for unprofessional conduct. Well, I'm sorry, but I don't think $5,000 is very much for the lives of 14 people who died in that accident. Now we go back again to my work on the onto the Nyaronga Pushbridge construction in 1980 to 84. We've already seen this photo of the northbound bridge, but here is this is the photo I wanted to show you. This is the southbound flyover bridge being pushed over the Hutt Road. And at the time, this was done without closing the state highway. I'm not sure that we'd been allowed to do it under the current health and safety laws, which are a lot stricter, but we did make sure that there was a lot of netting underneath the launch nose to make sure that nothing fell off during the launch process. The launching of the bridge usually took about 3 or 4 hours. The stroke on the 100-ton launching jacks was about 200 millimeters. So it didn't happen suddenly, it was a gradual process. And here is some of the background to the Nyaronga Pushbridge constructions in the 1980s. It was the first incrementally launched push bridges in Australasia. It was it was quite exciting to be involved in such a unique project. It was designed in the Ministry of Works Bridge Design Office by Howard Chapman, a very experienced bridge engineer. However, his design was checked by Leonhardt and Andra in West Germany, now Germany. They were the developers of the incrementally launched bridge construction method. We had a very detailed method specification because we knew that the contractor would not have experience in this type of construction. We had a large Ministry of Works team supervising the contractor for many reasons. The first one was we had a survey crew. Because the casting bed on an incrementally launched bridge, we had tolerances to achieve of 0.5 of a millimeter in both plan and elevation. And the reason this was important was, of course, we were launching the bridge 300, in the southbound bridge's case, over 320 odd meters on a curve with super elevation. And if you get the casting bed in the wrong position, the bridge ends up in the wrong position. We also checked every load of concrete. We checked the slump and all roading materials were tested. Despite all these checks, one pier on the northbound bridge cracked during the launching at the beginning of the incremental launching process. Construction was delayed 3 months while the northbound piers were strengthened. We stopped launching. In my view, the private sector would not have paid for this level of supervision, but consequences of failure were very high, crossing the main motorway to the Hutt Valley. In simple terms, failure was just not acceptable. Here are the details of what happened when the piers cracked on the northbound bridge as we were launching. And basically, if looking at my cursor, we got cracking in the corners where the peak loads were during launching. And the designers had to come up with a method of strengthening the piers in situ before we started launching again. And this photograph shows the work that was carried out. And as you can see, a large number of 7mm external pre-stressing was carried out. And these wires were installed hard against some machined steel surfaces which had been glued to the piers. And then the pre-stressing was post-tensioned by inflating 2 600mm flat jacks at each end of the pier with epiresin epoxy resin. And then after that, a concrete cover was cast around the external post-tensioning, and the finished bridge doesn't actually look like it's been strengthened. Now I move on to the Ruahihi Canal Collapse, which happened 24 hours after it had been opened by Prime Minister Muldoon in September 1981. And this was a major failure. It actually appeared on the front page of the New Civil Engineer journal in London. So looking at the causes of this failure, the canal was 3 kilometres long and 6 metres deep with a trapezoidal cross-section. The original canal design was concrete lined, but this was deleted to save costs. It took some researching to find this. I only actually found this when I was doing some more reading last night about it. So the original canal was unlined and was formed using compactive, sensitive volcanic soils. As I mentioned, the failure occurred on the Sunday, the 20th September, 24 hours after the official opening, although the canal had actually been in use for 4 months. The area that failed had persistent leaks prior to collapse. There had been some settlement in this area. Days before the collapse, the client told the local residents there were no serious issues. Fancy that. The area that failed eroded 200 linear metres of the length of the canal, and 1.5 million cubic metres of earth and water washed downhill and blocked the Tauranga to Hamilton State Highway. Fortunately, there was no loss of life during this sudden collapse, apart from 1,200 chickens that were drowned. To repair the canal, this involved shortening the canal by 500 metres and having a low pressure concrete pipe penstocks which connected to the main penstocks, and then lining the remaining canal with plastic liners and caustic and concrete pavers. The repairs cost $17 million and took 2 years, excluding loss of power, which was a 20 megawatt power station. So this was a major collapse. And since then, to my knowledge, very few canals in New Zealand have been built unlined. Now we move on to another dramatic collapse, the Hobart Bridge collapse, 1975 in Hobart, Tasmania. And this collapse was caused by a 35,000-ton bulk carrier carrying bauxite going upstream to the aluminium smelter which was on the Hobart River. And looking at the causes of the collapse, the main reasons were there was a strong outgoing tide, there were foggy conditions at night, and the captain of the boat was having trouble controlling the boat, and it hit one bridge pier, and when that bridge pier collapsed, it took 3 spans of the bridge with it. And as you can see from this close-up, some people had a perilously close call with death when this actually happened. 12 people died when this ship took out 3 spans. So looking to the future, how do we prevent this happening in the future? And probably a good example, which I like to use, is the Incheon Bridge, which carries a 6-lane freeway to the new Incheon Airport in Seoul, South Korea. I'm lucky enough to have travelled across this amazing bridge. It has an 800-metre main span, cable-stayed bridge. And the key feature I wanted to emphasise, which you can see from the cursor, is the large diameter piles which they've used to protect the main piers. And I don't know what size they are, but they look like they're 4 or 5 metres diameter. And they've erected them not only around the main piers, but alternative piers at the ends, so that any ship that's lost in the fog will hopefully hit one of the sacrificial piers rather than damage the bridge. Now we need to move on to a very sad disaster, Cave Creek on the west coast of New Zealand in 1995. I lectured on this collapse to over 200 people on a risk management seminars around New Zealand. And every time I talk about it, it makes me feel sad because there were so many opportunities to avoid this collapse. And on the left-hand side, you can see the faces of the 14 people who died in this tragic collapse of what should have been a safe structure to enjoy the view over the Cave Creek Gorge. This photo shows the Iroquois helicopter hovering over the gorge, extracting one by one the 14 fatalities. A horror story for New Zealand. The Kambath cantilever timber platform jutted out 40 metres into the gorge. 14 people died, all of them were students bar one. 4 were seriously injured, including one person who was confined, who broke their spine, is now in a wheelchair from Island Bay in Wellington. Here's a cross-section of the timber platform, and it was well designed, believe it or not. Typical timber platform with a cantilever, large 200 by 50 timber joists, which were designed to be fixed to bearers, which were bolted to the piles. And the other feature, which was, you'll see on my cursor, there were steel straps designed to strap the platform to the mass concrete steps. However, now we look at the causal factors. The causes and the missed opportunities. The platform was not designed or approved by a qualified engineer. However, if it had been built as drawn by the German landscape architect here on holiday in New Zealand, it would still be standing today. None of the people involved in building the platform were qualified engineers. The carpenter who fabricated most of the platform in the workshop fell out with the dock boss, and he was not involved with the construction at all. He was sent up to the north end of the Paparoa National Park to do track cutting instead. The piles could not be constructed in a straight line due to rocks. This would not normally be a problem. The bearers were supposed to be fixed to the piles with bolts. But as a generator was forgotten when they went to site, they couldn't use the drill, so the site team used skew nails instead. Some of the 4-inch nails which they used to skew nail had only 10mm penetration into the piles. Steel straps were drawn to attach the platform to the concrete steps as a counterweight, but these were never installed. No building consent was applied for the structure, and DOC did subsequently try and apply for a building consent after it was built, but a large number of conditions were specified which were too difficult, so they put the letter in the bottom drawer. A warning sign suggesting a maximum of 5 people had been made, but was not displayed. The platform had 18 people on it when it collapsed. 18! This was the last opportunity which was missed to avoid the collapse. The day before, an identical size group visited the platform, and the dock lady escorting the group thought the platform was not quite right. She thought it fluttered. She advised the dock person leading the group next day to inspect the platform before going onto it. He failed and ignored her suggestion and was one of the 14 fatalities. Systemic failure was given as the cause of the collapse. No one was prosecuted. Since then, the health and safety laws have been changed so that government compartments could be prosecuted. It's worth pointing out that at the time of the collapse, the Department of Conservation was a new government department set up after the folding of the Forestry Department, and they only had one registered engineer who was supposed to be responsible for the maintenance of 600 structures. I think you'd agree that's probably impossible. Now we move on to another sad collapse, which many of you will be aware of, the CTV collapse in the February 2011 earthquake in Christchurch. And as you can see from this photo, the lift tower at the end of the building, which was designed to take all the seismic load, survived the collapse. So, talking about the CTV collapse, 115 deaths from a single building collapse. It should never have happened. The building was designed and built in 1986. The designers were Allen Ray Consultants. The contractor was Williams Construction. I know from my experience repairing another Williams building that they had quality issues on other projects. The designer, Dave Harting, who I went through varsity with in 1972, had no multi-story experience. He was a civil engineer previously employed at Waimakariri District Council. He believed Alan Ray was supervising his design, but this did not happen. And frankly, he should have been aware this wasn't happening, because if you're doing a multi-story building design, you'd expect feedback every sort of 2 weeks or more, and not at the end of the job or something. The next point that's significant was the council engineer inspecting the consent application had raised several major design issues. However, Alan Ray pressured the council to approve the consent, and the council engineer was threatened with a loss of job if he didn't sign off the consent. The consent was approved. To give you an idea of some of the defects on this building, the column stirrups were only 6 millimeters diameter at 250 millimeter centers. Another significant fact was, following the September 2010 earthquake in Christchurch, the building was inspected and declared safe. However, the building occupiers who survived the collapse said the building really shook after the September earthquake when a large truck drove past. Now, it's possible that the wire mesh, which was the only connection to the lift tower, had failed on some of the floors. But of course, unless you lifted the carpet tiles, the crack in the floor would not be visible. The design was not to the current code, and construction was of a poor standard. The Royal Commission, who investigated this failure, recommended that designers focus on beam column joints, connections of floors working as diaphragms, and ensuring columns have adequate confinement to ensure ductility. Now we move on to the Mirandi Bridge collapse in Genoa in 2018. This was a major structure which collapsed in a storm. 41 people died. It was a very innovative structure for its year, because it was constructed way back in 1967 when it was opened. Had a 210-meter main span, was 40 meters up in the air. The bridge was structurally redundant, and all the stressing was carried in one large member. It carried 70,000 vehicles a day, and a lot of those were trucks. And the other significant factor was that there were deck cracks noticed 2 weeks before the collapse of the bridge. The lack of maintenance was determined as the primary cause. And another significant factor in this collapse was that the firm responsible for the tolls on this motorway bridge were also responsible for the maintenance. In this case, the toll company was the Benetton company in Italy, who some of you may know are probably more well known for their clothing manufacture rather than their toll bridge or bridge maintenance. Another very sad collapse. Now we move on to the Miami Bridge collapse, also in 2018. This was a very long bridge spanning across 8 lanes of traffic. And when it collapsed, there were 8 fatalities and 10 injuries. But lots of things happened prior to this collapse. The bridge was 53 meters long and it weighed 950 tons. It was a very unusual design. It's a post-tension concrete truss bridge. This was a design-build contract. FIG bridge engineers in the States were the designers. As I mentioned, this bridge spanned 8 lanes of traffic. The whole bridge was built off-site and lifted into place during an overnight lane closure. During erection, the north end cracked after some temporary pre-stressing was released. The contractor advised the designer of the cracking issue. 2 days before the collapse, the engineers proposed some remedial work, but did not consider it was necessary to close the road or prop the bridge. The engineer of record, which I think in New Zealand we would call the engineer to the contract, advised the Florida Department of Transport in a voice message of a minor safety issue. Unfortunately, the engineer who he left the message for was on a week's leave. At the time of the collapse, over the live highway, FIG engineers were meeting the Florida Department of Transport. The FIG lead engineer advised that the structural integrity of the bridge was not compromised and no safety concerns existed. Fancy that. And the bridge collapsed while they were having this meeting. FIG engineers did not know the reason for the cracks, but expressed no safety concerns. The subsequent inquiry concluded the bridge had design deficiencies, including an inadequate piers review, and the severe cracking was wrongly ignored by the engineer of record. The inquiry also concluded that one node on the truss was grossly underdesigned. As a consequence of this collapse, the contractor paid out $42 million to the victims and families of the tragedy. And I'm sure all of those would have preferred that their loved ones were still alive or didn't suffer the serious injuries they suffered. Now we move on to another New Zealand example, again a positive one for a change, the Centreport New Passenger Gangway in 2011, which I project managed for Centreport. And the reason I took a strong interest in this is that I was concerned that the gangway not only was properly designed and peer reviewed, but I insisted on load testing it because of a previous collapse in 1994 in Ramsgate in Britain. And this photo I still enjoy seeing because we're erecting it using the historic 1939 Hikatea floating crane, which in 2011 still has legally allowed to lift 80 tons. So the first thing to understand, if you're ever involved in a telescopic gangway, they are very complicated structures. They span across from solid land to a moving ship, and they can be carrying a large number of people. And the gangway for Centreport was designed to carry 5 kPa. And when I talk about the Ramsgate ferry collapse, 6 people died when that gangway collapsed in use. It was designed by a competent marine engineer, which had been certified by Lloyd's of London. When it collapsed, it was only 6 months old. Both the designer and the peer reviewer made the incorrect design assumption on one joint. This joint was assumed to be only loaded in shear, but it actually took torsion as well. So to make sure this didn't happen on my watch, I insisted on a full load test for the gangway, and the designer instructed that we needed to get 11 tons UDL on the structure. This was a bit tricky, but we ended up using bags of cement, which I borrowed from Wholesome. And as you can see in the photo, we did a 24-hour load test on the gangway, and this was successful apart from the deflection being more than the designer had expected. And so he instructed that an additional jockey wheel was installed to reduce the spanner fraction. And this gangway is still in use today, I'm pleased to say. The next thing I'd like to talk about is provenance and standards. All of you are involved with specifying materials, and you need to ensure that the materials meet the standards that you have specified. This is an example which caused us a bit of grief way back on the terrace tunnel. This is a large section. This is a 250 by 250 by 90 kilogram universal column section, which broke during pressing to form an arch for the terrace tunnel. And the top flange, which is visible by my cursor, is 25 millimeters thick. So when this flange broke, it made a noise like a mortar going off. And when we investigated this failure, we took a sample of this actual steel and discovered that it was well in excess of the 0.3% carbon that is allowable for mild steel, which we wanted to use for the bending of the sets. We checked the test results that had been supplied with this steel, and surprise, surprise, the test results said that the steel was compliant. Well, it wasn't. Now we move on to a mechanical engineering failure, but this was a critical component. And this is a 12mm copper pipe. And as you can see, rather than the wall thicknesses being symmetrical, on one side, on the left-hand side, it's almost 3mm thick. And on the other side, it's paper thin. It's only 0.3 of a millimeter thick. And you might think to yourself, well, if that was a water pipe, I guess there'd be a small leak. But this wasn't a water pipe. This was a pipe in the middle of a Qantas jumbo jet engine. And when this pipe broke, it squirted lubricating oil into a turbine that was also already going at a high speed. And this A380 had just taken off from Singapore airport with 469 people on board. And when the engine exploded, the explosion caused pieces of shrapnel to fly through the wing, which was full of fuel, and it also cut off multiple circuits. So the first thing that happened was that the pilot in command, Mr. de Kresny, practiced flying the plane for over an hour to see what he could do with it before he attempted to land. At the time, he had observed that they had no flaps, he could not dump fuel, and the plane did not turn like it used to. Fortunately, there were two additional captains on the flight deck, known as check captains, to check his performance, and they were able to assist in analysing the problems. Now, normally when you have a problem on a plane, you have 1 or 2 error messages. They had over 100. They did some calculations on landing the plane back at the 4-kilometre long runway at Singapore, and their first computer analysis showed that the plane would go off the end of the runway. The check captains then reviewed the calculations and realised that they'd input that the runway was wet, when fortunately the runway was dry. They redid the calculations. The calculations showed that the plane could land with less than 100 metres of runway to spare. And this plane successfully landed, despite the fact that it was running over speed, 50 tonnes overweight with no flaps. It burst 3 tyres during the landing. When it landing, it was leaking large volumes of fuel onto white-hot disc brakes on the wheels. The fire crew put out to reduce the temperatures of the discs. They then closed off all the engines, but one of the engines would not stop. In a nutshell, the flight crew decided not to declare an emergency evacuation of the plane because they knew that they would probably suffer fractures of the people leaving the upper story of the plane. And so they kept the passengers on the plane for nearly 3 hours while the fire crew controlled the situation. In the final analysis, the plane was subsequently repaired at a cost of $130 million, which was paid by the insurers, who probably claimed off Rolls-Royce. Qantas also grounded all their planes and discovered that 9 of their planes and some of other planes like Lufthansa had the same defect. So by successfully landing this plane, the pilot probably prevented further explosions, which would have caused other possible plane crashes. Conclusions. Well, as I said before, you learn from failures. And my key points are: design and construction is a team activity. Learn from those who have spent years in construction. Even better if you can supervise your own designs. Do not design anything before you understand how to do it or are competent in it. Ask for assistance or for supervision or assistance. And if your boss or supervisor is too busy or not interested, I suggest you look for another job. Do not sign anything you have not read or understood. Be inquisitive, raise questions, and if you do not get answers, elevate the issue until you are satisfied. Follow your conscience. If it doesn't look right, it probably isn't. Ensure materials and standards are met in the field to meet your requirements for your designs. Ensure specifications are written for the project. I've seen too many projects where the designers have done a cut and paste from a previous job and the specification does not make sense. Be wary of clients who do not want to pay for the required level of supervision. Construction tolerances may not meet expectations on your drawings. And a great example was the eagle that fell down at Wellington Airport. Be hungry for new ideas or information. Attend technical groups to expand your knowledge. Learn from yours and others' mistakes. Thanks very much for listening to this webinar, and I'll be happy to answer any questions. Thank you.
Thanks, Alex. That was really interesting. I always enjoy these lessons to be learnt because I learn a lot from them myself. We have just had the first question pop up, and it says, for the Nodonga Bridge, what's the cause of the pier crack during the launching of the girders? Has this not been considered during the design and not picked up during the peer review?
Yeah, good question. The answer to your question is a combination of factors. The piers were designed to be quite slender, so they matched the profile of the box. So there were some very high forces on the corners of the piers. And this was not picked up in the peer review, which was done by Leonhardt and Andra in West Germany. And I can't really answer why they didn't pick that up. But we did come up with a solution, and we did stop launching without carrying on, which is what happens with the horrible collapse at Injaka in South Africa.
One of the advantages, I suppose, of having high levels of construction monitoring on that project.
Well, also the fact, which I didn't realise at the time, was that the designers were only a 20-minute drive away. And that's why I think one of the causal factors of the collapse in South Africa was that it was a 4-hour drive to the site, and the senior partner was either too busy or couldn't be bothered driving. Effectively, he would lose a day by going to site to actually view the issues.
Yeah, we've had a bunch of people on there saying thank you very much for the seminar. I wanted to ask, you had maybe a top 10 of your of your tips for avoiding these sorts of things. If you could boil down, like a couple of primary causes of accidents occurring or these sorts of things occurring from your experience, could you boil them down?
Excuse me laughing, but there are quite often multiple reasons which are difficult to pin down, but the two which stand out in my mind are probably, first of all, human fallibility and pressure to meet either cost or program time constraints. The Ruahihi one, for example, the canal failed 24 hours after Prime Minister Muldoon had opened it. And yet the engineers knew that it was already leaking. I suspect that they didn't want to suffer loss of face by postponing the opening by the Prime Minister while they sorted out the leak problem. And so they went ahead with the opening, and it failed 24 hours after the Prime Minister had done this, even though the canal was actually 4 months old. So I think you've got to be very wary of pressures, both cost and time, and actually take a objective look at, have I got a serious problem? Do I need to stop work and sort out this problem rather than carrying on regardless? Does that answer your question, Martin?
And it does. And the next question that would lead on from that, of course, is, how would you advise guarding against those? So if you've got your main two being human fallibility and your second one being the cost and time constraints, what sort of processes would you suggest putting in place to try and guard against those? And what have you seen works?
I guess what have I seen works? Well, I was lucky enough to supervise some of my own designs. And I still remember a burly downer foreman coming in to see me one morning and crashing his fist down on the desk and saying, "Your name's on the bottom of this damn drawing. How the hell am I supposed to build this?" And I looked up to him with some temerity and said, "Well, Bert, I was 3 months out of university when I designed this drainage detail. Let's see what we can work out together." And so, if possible, it really is quite important if you can supervise your own designs, because one, you're the best person to be able to actually resolve problems, and two, you can learn whether or not your design is actually buildable in the field. And the example I showed of the terrace tunnel wall, which was supposed to be built from the top down, but because it had a very complex architectural finish on it, that was actually impossible. And the engineers in the future have actually learnt that, because when you drive down Caro Drive motorway on the southern entrance of the terrace tunnel, you'll see some nice architectural panels, but they were actually erected after the wall had been built with sprayed concrete, which doesn't look so nice. The architectural panels were erected afterwards. So I think when you're a designer, you always have to bear in mind, how is the builder going to build this design of yours safely?
That kind of ties back into making sure that you're doing adequate levels of construction monitoring, because it gets you out into the site, right?
Yeah, and the example of the 1-ton Eagle crashing to the floor, where Weta Workshop decided that they would do their own, they didn't need any engineering supervision, when their crimping tool was faulty, and when they erected the Eagle, they missed out one of the wires, and there were some design issues in terms of 4 of the 9 wires didn't have an adequate factor of safety. And so I think I mentioned in my talk that you need to be wary of clients who are not prepared to pay for an adequate level of construction supervision. And Engineering New Zealand has a number of different levels of supervision for various projects. And looking at, say, an incrementally launched bridge, that is a very high-risk project if it's going, even if it's not going over a live highway. If that fails during launching, you will have fatalities. It's as simple as that. Mm-hmm. And so the level of supervision has to be balanced, I guess, against how new or innovative is the design, how competent is the builder, what are the risks during construction. And as I've said before, design and construction is a team effort. The whole team has to work together for a successful outcome.
Thanks. We've got quite a few other questions here. And so the top rated one is, so far, I'm a firm believer in independent testing on concrete, yet a lot of specifications don't ask for this. What's your view?
Concrete's a variable material. As I mentioned at the Narong project, we slump tested every load of concrete. And fascinatingly, some years later, I met the concrete supplier at a social function, and I asked him over a few beers, what happened to the concrete that we rejected on your project? And on our project. And he said, I just used to send that concrete to another project that wasn't slump testing. So again, for critical materials, yes, I would agree you need to do independent testing. Nowadays, block tests are normally taken by the concrete manufacturer, and they have processes to make sure that they are actually audited so that their tests are kosher and not fabricated. New Zealand is fortunate in that the level of graft and corruption is relatively small, and I would encourage designers to actually visit the concrete plant and check out the laboratory that most concrete plants have and observe crushing of concrete samples, because trying to take your own samples and independently testing them, unless there are very specific reasons, is a very expensive process.
One question that we've got here, which I think is excellent actually, it says, how do we share knowledge of failures or difficulties encountered in a encountered in a collaborative and informative manner. And before you answer that, I'll just step in there if I may. And I don't know if you know, Americo, this is there's the CROSS system for structural engineering that's through the UK and Australasia. And we've actually got an article about it on the website at the moment with a latest system. The Engineering General Practitioners Group runs a, I don't know if you're a member of that or not, but it has examples in their quarterly newsletter of lessons to be learned. But I would also suggest writing in an article to the technical group that you're most involved with, you know, and so whether that be CSOC or the general or the geotechnical group or whatever discipline of engineering that you're involved with, those are the best kinds of ones, because, you know, Alex is very kindly sharing his knowledge, but it's everyday engineers. If we can share the type of experiences that we've encountered, then that's hugely beneficial in my opinion. Over to you, Alex.
Yeah, I think it's important that you do share both successes and failures. I was fortunate enough to actually lecture on the Naronga flyover construction to some engineers in Japan. And in those days, of course, we were using slides in a darkened room. And as I showed the slide showing the cracked pier and the strengthening, I heard gasps in the back in the room. And I asked my translator, can you ask them what's the reason for the gasping? And the answer came back, oh, we would never show slides like that of failure in Japan. And so I think that probably answers the question that you need to learn from mistakes, because one other article I read was that some mistakes have a habit of recurring every 30 years because people like me retire and the next generation of engineers come along and they fall into the same trap that we might have fallen into 30 years ago. So I've always been a firm believer of actually talking about successes and failures. And even today, while I was out walking the dogs, I'm supposedly semi-retired, but not. I had a call from a friend who was asking me some questions, would you believe it or not, about the Naronga bridge bearings, and also about a corrosion issue on another project. And so the important thing is to keep sharing knowledge. And I guess that's one of the things I'm a bit saddened about the demise of the old Ministry of Works, because there were always people there who were experts in particular fields, whether they were bearings, corrosion, bridge design or whatever. And without the issue of professional fees, you could ring people up and share a problem and get an answer.
Speaking of which, I have often found that even with the experts in the field, you know, if you see somebody's name on a paper or on a standard or something along those lines, you can frequently, New Zealand's a small community, it's great from those sorts of ways. You can frequently pick up the phone and they'll be able to share that, and they're willing to share their knowledge with you the vast majority of the time.
Yeah, you're right. I mean, if you use the phone, I think email's a bit of a trap. I mean, you need to talk to people because people regularly ignore emails, and there is no substitute for talking to people and having a two-way conversation, and you get much more detail that way.
Yeah. Now, next one, how frequently are the bridges in New Zealand inspected for maintenance, and what sort of process is used?
Sorry, I can't answer that question. You'll have to talk to Waka Kotahi. I know they have maintenance contracts for all their structures because the Tieback wall, which I designed and built, has got a missing cement panel covering some of the anchors, and I emailed Waka Kotahi and got a response back from their structural maintenance person, who in this case works for WSP. So I know they do have maintenance contracts and inspection procedures. I just don't know the frequency, other than the fact that after the Bulls Bridge scour failure, I know they inspect scour quite regularly on bridge piers.
And what are your views on the self-certification philosophy adopted in the industry?
Good question. Self-certification I think is a little bit of a, I think it's been invented by an accountant, to be honest. It's to save money. I think self-certification is probably okay for minor things that are not unusual, but certainly anything which is complex or unusual needs to be peer reviewed by somebody separate. And in most cases, that really needs to be somebody from a separate company, because somebody within the same company is automatically likely to review that design with somewhat rose-tinted glasses.
Yeah, and on that topic, as someone who gets asked that question on a fair amount, a peer review cannot be conducted by somebody that works for the same company, even if you work for an office in a different part of the country. You don't have the level of
independence.
Independence, thank you. That is required. And so next one would be, what are some of the technological advances over the years that have helped prevent potential disasters, and where could it be improved still?
When I was designing the Tieback wall, I used punch cards for the design, and some of my designs took 135 minutes overnight on the IBM mainframe on the terrace. So certainly computers have made things a lot faster. Cell phones, I think, have also improved communications. Communications are much better because nowadays people can send photos and videos of problems from remote sites, whereas in the old days, you may not even have had a phone. I can still remember when fax machines cost $10,000 and our office didn't have one in the Ministry of Works, and we had to go to the local post office to send a fax and then ring somebody up at the office at the other end and tell them to go down to the post office and pick up the fax. So we've got much more instant communications, which is actually a plus. I think the downside that has happened is that there is this continual desire to do things for less cost, and less cost means less design fees and less construction cost and less construction supervision costs. And I'm sorry, but the old phrase that if you pay peanuts, you get monkeys still sticks in my claw.
Yeah, I agreed. And some of the failures that I've seen through the reports that I've been reading, in particular going back through the Canadian one in 1988 with a supermarket roof collapsing, and their design fees were 0.25% of the total costs. Where it should have been up around sort of 7 to 8%. They found in the commission of an inquiry. The other thing that we find is that you mentioned computer modelling, but you've got the garbage in, garbage out, and a lot of people now, we have found, go straight to a computer model as opposed to sort of hand sketching out just identifying the load paths and then sort of building the model from there.
Yeah, you need to
assume that if you were going to be doing something that had 135 hours of feeding things in with punch cards, you probably would have sketched out your model first to make sure that it worked.
Well, the thing with 135 minutes process time was that every punch card had to be 100% accurate, otherwise the whole run bombed out. And I actually worked out that to focus on making sure those cards were correct, I had to check them after 9:30 in the morning when I'd fully woken up, and before 3 o'clock in the afternoon, I was starting to think of what I might do afterward. So I guess as individuals, you need to know your strengths and weaknesses, and I don't think there's anything wrong in actually acknowledging that. And but going back to this whole issue of fees and cutting corners, I think it's important that people stand up and be counted. If they're doing a complex structure, they should just dig in and say, no, I'm not going to design it for those number of hours or fees. It's just not possible to do it properly.
question that's been voted up. It says, do you think that a graduate structural engineer should be trained on site before he or she starts to design?
No, I think it's a combination of both. I started off in a design office it's actually 2 years before I went to site. It probably would have been beneficial if I'd had some site experience after a year. When you do your university degree, you have 3 periods, well, at least when I did it, I don't know if it's still the same, probably is. You had to do 3 periods of supervision. One was mechanical workshop, even though it was a civil engineering degree. One was a civil engineering labouring position. And in my case, I was lucky enough to go to Takanu Power Station in Turangi, where the guys in the workshop took delight in playing practical tricks on me. And then one period was some responsible engineering experience where I worked actually on shell gully structures behind the terrace, and I was the surveyor in the Ministry of Works team. So as long as that is still applicable to an engineering degree, I don't see a need for designers to go to site straight away, but I do see benefits in them going to site after, say, no more than a year.
Thanks. We've got 3 questions left, and then we'll call it quits for there, because I've got another meeting coming up and I haven't had lunch yet, frankly.
Me too.
And so when some site contractors are not happy when subcontractor advised some extra false works should have been planned prior to erection, as per the health and safety guides. Any recommendations and advice?
Yeah, false work's an interesting one, because I had 2 occasions where I actually personally inspected false work before a major pour on both the terrace tunnel and the Narronga gorge overpass by the old LV Martin site. And in both cases, I found screw jacks which were not fully engaged. And you go back to this whole issue about design and construction being a team effort. And ultimately, when you do false work design, every piece of scaffold tube has to carry the same load. And if 1 or 2 of them are not screwed down and engaged, that means you're going to start overloading the others. If the subcontractor raises an issue of health and safety, if I was the supervising engineer, I would probably ask what the issue was and see if I agreed with him. And if I did agree with him, I'd basically say to the main contractor, I'm not signing off the project for a concrete pour until these additional measures are taken, because they're usually quite small in terms of the whole project costs, and the consequences are probably large.
And so second to last, it's re-pressure on cost and duration. Perhaps the word that's fallen too far from use is quality in all its senses, which is more of a statement than a question, but
well, quality is part of conforming with your specification, and that relates to supervision and costs. Quality is part of the final outcome for a project, and quality is also part of your specification documents and the materials you used. I haven't used quality much because to me it's a given. You nominate what finish you want in your concrete, you nominate what strength you want in your reinforcing or pre-stressing steel, and you check that those materials meet those quality requirements. So for me, quality is a given. It's part of the process in terms of the design and the construction.
Well, good. And the last one's more for me, actually. It says, great presentation, Alex. Thanks to all. And hi, Martin. I think you may be mistaken on the peer review process for bridges. Waikatahi sets our requirements for peer reviews. Waikatahi does allow independent peer reviews of structures within the same company, but from a different office. Must obviously be an independent / team reviewer. Possibly they do. I know that with our peer review note, practice note 2, then our policy is that, as I stated before.
Right. No, well, I mean, at least it's getting a peer review. I mean, as I noted with that Florida bridge collapse, and the Injaka had no peer review, and the Florida peer review was inadequate. So the important thing that there is a proper peer review, and at least if it's in a separate office, they're more likely to pick something up than in the same office.
Well, we'll close it there. Thank you very much. I really appreciate your time. There have been some suggestions in there for perhaps a future webinar dedicated more to bridges or solely to bridges from you. I don't know if you'd be interested in doing that one, possibly in conjunction with the bridges group. I don't know. Yeah,
I'm going to a bridges meeting tonight. So the paper was originally written just for bridges, but it was impossible for me not to include Cave Creek, which isn't technically a bridge, because there were so many lessons learned on that one project that I consider it essential to include it. So no, I will continue talking on failures, both bridges and others, for probably until people think I'm too gaga to actually say anything further.
Well, hey, look, thank you very much for your time, and enjoy the rest of your day.
Thanks, Martin, and goodbye, everyone. Bye.